you in a Pope si chiamava, Enrico, il libro. Okay, Pope. I was talking about a book that Enrico and I were speaking. Sì. And it was named Pope, P-O-P. It's a nice book for turbulence. What do you do? What do you say? Start?
You said 5 minutes.
5 minutes?
Yes. We should start then.
Slowly. Let's start slowly. Okay. Last lesson. Last lesson we try to conclude the stratification part, and in particular we try to include the concept of turbulence again. So we won't talk about turbulence extensively because this is not part of the course, unfortunately. But I'm sure that you will have to cope with it because turbulence is a very fundamental part of GFD. So actually, when you talk about currents and currents in the ocean, or weather phenomena like cyclones, of course, you can always take the large scale and try to describe everything, well, everything from the point of view of the large scale by using geostrophic flow or the perturbation theory that we looked at a few days ago with the barotropic waves. But of course, when you go down and you want to, of course, increase the resolution of your phenomena, you need to cope with turbulence. And as I told you last time, when you have, since I think that probably all of you will work with the numerical modeling. So usually numerical models are they describe our Earth planet with a grid, okay, with a mesh, which usually can be regular, but in other case, for example, if you, especially for sea basin, so where you have land here, and for example you have a town here, and you want to, for example, there are factories, and you have some pollution. So in this kind of situation, of course, GFD becomes quite unuseful, and what we talk is about environmental fluid dynamics. Okay, and what we do here usually is try to refine as much as possible the mesh in order to reach the dimension of the smallest phenomenon. And in a representation like this, it's important also to take in account. Okay, very good. We were just talking very generally. It's also very important to take in account chemicals. Okay, so of course, for example, the RegCM model that all the people in the Filippo Giorgi group are using, RegCM has a module for chemistry in the atmosphere, okay, which is extremely important because when you want to explain climate change, you know that climate change is based on the interaction between chemicals like CO2, like methane, like sulfates in the atmosphere, okay? So you need not just to consider the physical part, but also the chemical part. And if you are interested in the, let's say, liquid part, which is the sea or the ocean, the sea, lakes, or bay, or small basins, lagoons, for example, you also need to include the biological part, okay? That's why most of the community now are working to what we call Earth system models, okay? So Earth system model take into account atmosphere, ocean, chemistry in the atmosphere, chemistry in the ocean, land, so forest, for example, different kind of impact of human activity on the territory, and then biology in the ocean, okay? Of course, putting everything together is not so easy, but at the end, this was the goal of this introduction, is the fact is that when you want to represent phenomena which are smaller than the grid dimension, okay, like if you take delta x and delta y, and delta x, for example, is 10 kilometer or 5 kilometer or whatever, in any case, you will always have processes that will be within this. If you remember, one of the first lessons that we did was we showed this this plot here. Okay, so in this plot, come on, yes. So in this plot, you see that most of the phenomena which are, let's say, shorter than 1 hour, so within the Rossby limit, and shorter than 1 kilometer, are actually the one which mostly affect our life. Okay, so boundary layer, wind at sea, and here we have like cumulus convection, thunderstorm, boundary layer turbulence. Okay, so the smallest is the grid. The highest is the probability that your model will be able to describe your reality in a better way, an improved way. And of course, the challenges that our community are facing in these days, actually, is the challenges are mostly related to increase the computational power of computers, but also to improve the models, so the numerical cores of the model, in order that they could be able or to resolve fastly the equations, or to include more processes. Okay, so if we consider, for example, a space where we have here the resolution delta x, so increasing resolution. Here we have, for example, the processes, physical, biogeochemical, chemical processes. Here we have the integration time, which means also the presence of ensemble simulation, which are very important when you want to make a climate prediction. Okay, if you want to make climate prediction today, people don't use just one simulation and one model. They want to have many models, so different recipes to describe our system, our planet system, with different philosophies. And they want to put everything together in order that if you want to, for example, simulate the increase of temperature, you don't have just one realization, but you have many realizations. Okay, and so at the end you can say, okay, the mean, the average is this, with this uncertainty. Okay, which is extremely important. Okay, the definition of uncertainty in climate prediction is extremely important. Okay, so if you consider something like this, you can create like a sort of, let's say, plane, okay, which increase according to the number of processes that I want to solve. The smallest of the resolution, and the highest is the number of the integration, or the number of ensemble. Okay, so this sort of plane measures, in some sense, the complexity of all the air system modeling. Okay, so this was just a sort of introduction to wait your arrival. Okay, so to conclude what we looked at yesterday, that, as I told, was not including turbulence. What we want to do now is to try to include turbulence, and in particular we want to introduce a quantity which we already found when we look to the Ekman layer. If you remember, we considered the Ekman layer when we are in turbulence with this specific parameterization. Okay, so where there was like a number 0.4, okay, which was a little bit different from the classical representation that we have when we just put Ekman equal to 1 and we obtain something which is basically depending on the viscosity. Okay. So we did it. We just touched the surface with the Ekman layer. Let's try to look a little bit more in detail now. So we defined yesterday the value of the mixing layer. Okay, so you remember that when we had the Kelvin-Helmholtz instability, we said that every two-layer system is always unstable to the shorter waves. Okay, and we found the expression of the wave number, of the critical wave number, and then we related the height of the thickness of the mixed layer with the wave number, and therefore with the wavelength, because we know from experimental that the typical pattern of the Kelvin-Helmholtz stability has the horizontal dimension, which is has the same order of the vertical one. Okay, so delta H more or less like lambda max. Okay. So delta H was defined as rho 0, the square difference of the two velocities. Okay, so we are still in the two-layer system, divided by rho g and the difference in density. Okay, so if we include this expression here, which I remind you, which is called the friction velocity. Okay, so friction velocity actually is a measure of the variation in the velocity. So if I have, let's say, a shear like this, okay, U1, U2, the difference between the two, I can represent it as the friction velocity. Okay, so intuitively, you can say that if you have a fluid like this, and you have, like, for example, looking from above in the river, okay, that we talked last couple of lessons ago. So you have that there is a flow faster here, slower here, and what you have is something like this. Okay, so just put it in the vertical, because we are working now with the vertical dimension, because we are working with variation in density. And we can represent that the variation of velocity, so this term here, can be scaled like the velocity friction. So the difference in, so this will be like delta U, which will scale like U star. And this will be, our delta. Okay, so we can say that this is rho 0 U star over G delta. So if we multiply this square, if we multiply up and down by U star, what we obtain here is a third power, and here we have a multiplication which is between the variation in pressure and the scale of the variation of velocity, which is the friction velocity. So this term here can be written as this term here. So now I'm taking a very big freedom, okay? So I'm saying that the multiplication of a friction velocity, which actually is in this direction, but actually correspond to the velocity of, let's say, this eddy, okay? This is an eddy, okay? It's a typical system that you can have in a stratified system, okay? So I had said that U star is the scale of the variation of velocity, but U star actually is the scale of velocity of an eddy which is living in the stratified system. So what Cushman says is, let's consider this term here as a turbulent transport of vertical turbulent transport of perturbation, of density perturbation. Okay? So delta rho can be in some sense represented as a density perturbation. U star can be represented as the perturbation of the vertical velocity. And what we obtain is a turbulent, actually a turbulent measure. And you can, if you work on the density equation, the general one, but more or less you will obtain that if you don't make any kind of approximation, because we did a strong approximation, we linearized our equation, but if you keep the approximation, if you work with your Reynolds average Navier-Stokes equation, you will find that you will find some terms like this, or for example like this, or like this, or also like this. Okay, so these are practically multiplication of perturbations, which are called the Reynolds stresses, which actually take in account the role of the turbulence in the fluid, in the flow. Sorry, not in the fluid. And these, of course, are a very important, very strong and important problem to be solved when we want to put our system in a numerical description. Because to describe this, you need the so-called subgrid parameterization. So, I mean, parameterization that explains you what happened when you are inside your box, your numerical box. Okay, so these live with scales, temporal scale and length scale, which cannot be resolved by the numerical system, by the numerical models. That's why we have to parameterize. And for example, say that U prime, W prime will be equal to a certain alpha, for example, du bar dz. Because I know U bar, I know the average of the velocity, but I cannot represent this. Of course, this brings an error. So the uncertainty of the numerical model increases because we are not able to represent the correct expression of the Reynolds stresses. Okay, so this actually the Reynolds stresses also have a statistical meaning, because they are nothing more than the correlation between the perturbation. So let's make a step ahead, and what we obtain is something which is third, and then we have G, W prime, Rho prime, and we also put a K, which is again the von Karman constant, 0.4, and what we obtain is this. So this is like this, and we put a capital L here, and this is a new definition. It has a, of course, we just started from the description of the mixing layer, and we obtain again a distance, which of course is positive, and means that if it is positive, since all these terms are positive, W prime or O prime must be positive. So what does it mean, just intuitively? It means that if I have a stratification like this, which means that I have heavier fluid here on the bottom and lighter fluid on the top. So the action of the eddies is to bring a parcel which is heavier here up in the towards the top part of the system, and a parcel which is here, which is lighter, down. Okay, and this is exactly what our correlations say. So it means that in the general system, in the general turbulence of the system, what we have is that parcel which has vertical velocity perturbation positive will be correlated to density perturbations positive, and vertical, so W prime positive will be correlated with rho prime positive, or W prime negative will be correlated with rho prime negative. So parcel with the vertical velocity perturbation positive, which means that are going up, will bring density which will be larger than the mean, so with positive perturbation, so which means exactly to bring heavier fluid up, and the contrary in the other side of the empty. Okay, so this expression here is called Monin length, and actually is derived from the definition of our mixing layer. So it means that Monin-Obukhov length actually is the vertical distance of the larger eddies. Okay, so if we have a stratified flow where we have a velocity shear which is going this direction, so it means that we are taking parcels, heavier parcels, and we are upwelling them, and lighter parcels, and we are downwelling them. Okay? This means that L actually is a measure of the distance of the scale of our eddies. So the eddies which are constrained both by the stratification level of the system and by the velocity shear which is applied to our system. If we describe rho as rho 0, 1 minus alpha t minus t0 plus beta s min minus s0, so it means that we are going to describe the density in the ocean, and we just consider the effect of the temperature, so we can neglect this. We can say that actually W prime rho prime is written as alpha rho 0 W prime T prime. Okay? And this means, since we are going to, we can rewrite L, and L will be rho 0 U star to the third kg minus alpha rho 0 W prime T prime, so rho 0 can be removed, and what we obtain is this one, so we can write it here. And of course, since still this is positive, it means that W prime T prime must be negative, which is exactly the same thing, because we have colder, so temperature, so we will have the correlation between W prime positive and T prime negative, and the contrary. Okay, so W prime positive, it means parcel going up, upwelling, which will bring cold temperature up and the contrary on the other side. Okay, so this is actually the idea of how the stratification is actually eroded at a very high scale, very small scale, and how the turbulence act to erode the stratification. Of course, on one side, the turbulence act to erode the stratification. On the other side, the stratification tries to restore the balance, the initial balance. Because if you stop the velocity shear, of course, the eddy are completely start to disappear, and there will be no any kind of energy source in order to create the instability, and so we will come back to the initial situation. Okay, so we can try to help analyze some example.
Excuse me, Professor.
Sì.
I don't quite understand what is the role of the numerator in the length scale. The denominator is, we have said, a measure of how the turbulence tends to stabilize. Yes.
This one?
In L. Yes, it's the same.
Well, this is a sort of, well, this is
The upper is a flux of momentum.
development.
Yes, of linear momentum along the direction of the mean flow flux.
You mean this one?
Yes, the
Okay.
term
Yeah.
u star to the third power.
Ah, you don't, well, this is the,
I mean, that's a ratio of two fluxes.
this is not exactly the ratio. So we started from delta H. Okay, it's actually a ratio, of course, but it is not,
Yes, it has a dimensional length.
exactly, it has a dimension of a length. So we are not making, it is not like the Richardson number, where is the ratio, I mean, which has the physical meaning of the, let's say, potential barrier against the kinetic source. This is more related to the fact that we transformed a macroscopic length, which was related to the Kelvin-Helmholtz instability, to something which is which has more relation with the turbulent transfer of information. In this case, of temperature. Okay. So what we did here was just to transform, to give to the difference of velocity, which actually is a perturbation of velocity, because this is greatly exaggerated, of course. Okay. We can have this, which is like, for example, like this, or even like this, and so the U star is very, very small with respect to this one. Okay, so this means that in general you will have like eddies like this, like this, like this. But the maximum value that you can have in a certain system, in a certain moment, certain instant of the evolution, is related to actually the value that you can have from the friction velocity. And friction velocity, as we will see now, is directly related to the external source of energy that is imparted to the system. Is it clear? We can discuss later. Okay, so example. This example is very interesting, and actually this was one of the exercise, if I correctly remember, of the exam last year, and relates so it's a problem that wants to solve the height of a mixing layer which is produced by the action of the wind stress over the sea surface. Okay? So this system will have at the beginning, at t equal to 0, a constant density value, which is expressed like this, so linearly increasing in z. But after the wind stress act to erode to erode this, this layer, we will obtain a layer which will have rho 1 as a constant density over the height h, and then for z deeper than h, we will still recover the initial density gradient. Okay? So, starting with the wind stress, eroding the stratification, creating a mixed layer of depth h, and then, I mean, this, of course, this action starts in a very thin layer close to the surface, then gradually propagate in time up to reach a certain level of depth. Of course, if the wind stress stops, it recovers the initial configuration. Okay, so we know that the value of density is equal to minus rho 0 m square gz. So if we have only this kind of forcing of our system, so we do not have any kind of surface heating, so no fluxes, no precipitation, no evaporation, we can calculate the effect of the wind stress by considering that rho 1, which is the density at the end of the let's say, destruction of the stratification in the mixed layer, which will be practically the average between rho at z equal to 0 and rho at z equal to minus h. Okay? So, exactly as we did yesterday with the two-layer flow, we calculate the final density, which is nothing more, so I have just to substitute minus h here, divided by 2, and I obtain rho 0 m squared h over 2g. So there is a strong discontinuity in the density profile, because the density profile is constant here, and then there is a jump from here to here, and then again the density increase linearly. So the density jump delta rho, which is rho 2 minus rho 1, so rho 1 is this, rho 2 is simply rho when z is equal to minus h. Okay? Because it is exactly the same value of density that the system has at the base of the layer. So, which will be exactly equal to this value. Okay? So, the density jump have the same value of rho 1.
But this density is 0 at the surface.
Density is 0 at the surface, yes. This is always our rho prime. Otherwise, yes. Good. Because otherwise we couldn't have. So our density is rho equal rho 0 plus rho prime, and this is rho prime. Because otherwise this is given by the fact that you have m squared equal minus rho 0 g d rho dz. Okay? So considering this like rho over z, of course this is delta rho, so it's a density perturbation. Okay, so we want to understand what is the potential energy that has been gained again, as we did yesterday, the day before, in the period t. Because what we want to know is what is the value of h after t. So we start from the situation at t equal to 0, where we have the linear density perturbation in depth. Then we have the effect of the wind stress, and after some period t, we will obtain a value of h. So this will be the difference between the final density, which the perturbation density, ρ1 gz dz, and what we had at the beginning, which was ρ function of z gz dz. Okay? So the final potential energy value and the initial potential energy value in the layer equal h. So if we substitute and we do all the math, what we obtain is 112, because here in rho z I use this expression here, okay? So 112 rho 0 n squared h to the cube. So of course h is function of t, because we are not in a steady situation, but we are analyzing how the system is evolving. So we can look for the rate of change of our potential energy, which is nothing more than 112 rho 0 n squared, and then I must do the time derivative of h cubed. Time derivative of h cubed is nothing more than h squared over 3h squared dh over dt. Okay? And so this will be 1/4 rho 0 n squared h squared dh over dt. Okay, now we know that the rate of potential energy, so the change of the rate of potential energy, which is positive because these are all positive terms, and this, of course, is increasing in time because h will start very small at the beginning, very, very thin, and then the layer will increase in time. So we must consider that the variation in potential energy will be given by an energy, a source of energy, which is the wind stress, the only energy that we have in this, at our disposal. So, wind stress tau, which is equal to the multiplication, to the product between the density and the friction velocity squared. Energetically, the rate of work that tau is producing over the system is just tau multiplied by u star. Okay, so if you don't forget your mechanics lesson. So when you have a stress, if you multiply a stress by a velocity, you have a rate of work. Okay, and so you obtain rho 0 u star cube. So all the wind stress is transferred to the system, but of course we cannot say that the rate of work is exactly equal to the rate of change of potential energy, because a portion of the kinetic energy that is transferred from the wind stress to the system has gone in dissipation. Okay, so we can make the balance between the variation of potential energy, and then we will put a coefficient m in front of the rate of work given by the wind stress, in order to take into account that not all the energy that is transferred from the wind stress is directly transferred to the potential energy of the stratified system. But one part is also diverted to dissipation and to actually creation of kinetic energy, transfer of kinetic energy, in the fact that there is some dynamics here. I mean, there is not just all the energy which is converted in the destruction of the stratification. So we can equate these two, and we can have actually a way to solve dH over dt. So if this is equal to m rho 0 u star cube, and then we have delta h from 0 to h, which will be equal to dt from 0 to t. We will have here the only term which depends on h, which is h squared. Then we will have rho 0 n squared, and here we will have 4m rho 0 u star cube. Okay, so rho 0 and rho 0 can be neglected. We just solve the integral. And what we obtain is h cube over 3, which is equal to 4m u star cube over n squared, which means, and then we have, which means that we can have a 12 here. And at the end, we can write that our h dependent by 8 will be 12 m t over n squared to the 1/3 multiplied by u star. So ht grows linearly with the u star. So of course, the stronger is u star, the larger will be ht. It increases according to a 1/3 power of time, and it is obviously inversely proportional to n squared. So the largest will be this one, the smaller will be this one. Of course, the larger, the stronger the stratification, the most difficult will be with a given u star to destroy the stratification and to increase the h. Okay? Okay, so this is called like instantaneous mixed layer depth or thickness, as you prefer. So can we able now, are we able to create a link between this expression here and the Monod-Nabokov length? So the Monod-Nabokov length had this form here, but also the previous one, which was rho 0 q cube and qg W prime rho prime. So let's try to estimate for this problem each of these, the only term that, because we have U star, we have all the other parameter, of course. Let's try to estimate the turbulent transfer of the density perturbation. So the scale for the W prime will be dH over dt. Okay? So the scale of the vertical velocity is practically given by how the instantaneous mixed length change in time. The scale of rho prime is obviously delta rho, which is our density jump. Okay? Over there, of course, is strongly exaggerated. So delta H over T, it was somewhere. It was here, but okay, we can use it. So it's here. It's 4 m rho 0 U star cube over rho 0 n squared H squared, while the scale of delta rho is this one, so it's rho 0 n squared to G, and then we have H. So we can neglect n squared, very important. We can also neglect remove 1h. We can also make a substitution like this, and what we have is m U star cube rho 0 over GH. It's much easier from the desk to, to follow. Okay, so let's try to see our mononomial of length. So is rho 0 U star cube over kg, and then we substitute 2 rho 0 m U star cube, and then here we have GH. So rho 0, U cube, G and G, and we have H 2 Km. Okay? So, very good. We have that L and H actually have the same order, but if we take some specific value, so we know that K is 0.4. One special case, but Cushman said not so special, can be observed, is that M is 1.25. So if you substitute this, you obtain exactly H. So Cushman say it is for tissues. In effect it is, because personally I'm always being a little bit critical about that. And I'm not still very clear about how he explained the expression of M on this. And yesterday and the day before that I reviewed this lesson, I always be a little bit not very convinced, and so I decided to write an email to him, so that for the next year maybe I will be more confident. But by the way, in any case, even if this is, let's say, a number which is order of 1, in any case what we obtain is that the mononomial of length has the order, or even in this case, is exactly equal to H. Okay? So the mononomial of length, which was derived before as a sort of turbulent expression, turbulent configuration of our mixed layer, actually has turned as the value of our instantaneous mixed layer depth. Okay? So mononomial length actually describes the vertical distance which characterize the vertical eddies, which creates the, which destroy the stratification, and are actually confined between the balance that we have between the wind stress, which destroys the stratification, and the stratification itself, which acts to counteract the destruction of itself. So it's like a fight to survive. Okay? So this is a system that is very typical observed in the ocean. Of course, you can also observe it in the atmosphere if you consider like different layer of the atmosphere. So you can destroy, for example, one specific layer of stratified atmosphere with the action of the wind, which is in the layer above. But one of the most typical effects related to stratified flow that appear in the atmosphere is the convection. Okay? So we will see three distinct examples of convective motion. And convection actually is different from this example, because while here the destruction of the stratification was due to a real mechanical action. Okay? So there is a mechanical action given by the wind stress that destroys the stratification. For convection, there is no mechanical action. The only possibility is that it's the buoyancy itself, due to the fact that we have a different, let's say, a sort of instability in the thermal profile that creates and tries to destroy the stratification. So what happened in our Earth is that even if we are on the land or if we have in the sea, when our sun hits the surface, what happens is that both the Earth and also the ocean re-emit infrared. Okay? During the day, you have, according to the presence or less of cloud, but if the clouds are absent, you have direct radiation. I can neglect scattering, of course, given by the gas in the atmosphere, but in the very most the easiest approximation, we have just radiation coming down and radiation, long wave radiation. So we have short wave and long wave radiation, which is like the infrared, which is actually the one which satellite can sense, for example, to measure the sea surface, the temperature of the sea surface. So it means that the first layer of the atmosphere is constantly heated by below. So it's like we consider two plates, one at temperature T2, one at temperature T1, where T2 is larger than T1. Okay? So this is something, as a layout, a configuration which is prone to instability, because we have hot, warm air fluid, let's say here, and cold fluid here. Okay? What we know is that cold fluid is heavier than warm fluid, so we can expect that this will go down and this will go up. But let's try to keep this to the very simple case. And what happens is that if this is the case, so what we have is that we will always have a layer which is called atmospheric boundary layer, or ABL, which during the day is always heated from below. So we have no mechanical action, there is no wind in this case. The only driving force in the system is given by the buoyancy. So the fact that we will have pack of airs that spontaneously, because of the effect of the short wave which goes to the ground and then is remitted, actually start to go up. And of course, if there is the right condition, like in summer, when effectively we have a system like this, where we have, for example, very cold air here and very hot air here, what we obtain is a system like this. Okay? And system like this create thunderstorm. Okay? So it's something is a layout, a configuration which always happen, quite often happen, for example in summer after afternoon. So when you have the maximum of insolation, so the maximum of energy which hit the ground, and so you have the maximum of the UV emission, and so this delta T, which is created between the surface and a certain height where you have the temperature cold enough, is sufficient to start the condensation of the parcel, of the air parcel, and the creation of thunderstorm and then rain. Okay? So, of course, as I said yesterday, this kind of situation, which should be the normal one, can be destroyed by the fact that during night, what I have is that there is no, of course, shortwave radiation, but I have a cooling. So the ground is going to extract temperature from high temperature from itself and moving it upside in order to cool the first layer. So if we have a stratification profile, which is not this case, for example, given by the fact that we have fog, this situation here is not permitted, and what happens is that during the night the fog is formed, and the day later, for example, if we have cloud, so part of the energy is reflected, so there is not enough energy to destroy the fog layer, and the fog layer acts as a sort of insulation for the ground. And what happens is that you have the thermal inversion. Okay? So you have that here, temperature actually is colder than what you have here, which is something which usually should not happen, because if you go up in the mountains, you have the temperature is colder. And this is related to very, in any case, a short layer, but it is extremely typical in urban environment, where you have, like for example, Mexico City. Mexico City is a huge town with a lot of industries, a lot of cars, and is in a sort of valley. And so you can have, since you not just have this situation, but you also have mountains here which do not permit efficient renovation of the air within, and so you have a lot of pollution. So people really die over there, okay? Because of the pollution that they had to inhalate. But this can be also, for example, in Trieste, during Sundays, or as I said the other day when we talk about the blocking, is something typical in the Po Valley. Okay, so if we consider again this situation, we can make one more consideration, and consider that the movement of a parcel, warm parcel from here to here, can be in some sense retarded by two effects. One is the viscosity, and the other one is the diffusivity. So, if we do not have any kind of turbulence, if we have just the variation of T is very small, very close to zero. So it means that T2 is slightly warmer than T1. Okay, so there is a very short, very small gradient of temperature between the two plates. The only possibility to transfer heat is by diffusion, or, as we said, conduction. So by conduction, which is actually a molecular phenomena, we just transfer very, very slowly the information of heat of the plate T2 to a layer which is slightly up with respect to the boundary. But in absence of other forcing, there will be never the possibility to create a complete mixing of the system. Okay, it's like in the previous case, the fact that we have simply a system that is completely stratified. Of course, in this case, the system is not like this, but is more or less like this, because here we have a temperature which is warmer, so it means that has a very the variation in density is very small with respect to the parcel that we have here. Okay, but the fact that this system is not unstable enough to create instability is like we said yesterday, that we have not enough stronger perturbation, so there is nothing that is traveling within to create, because we don't have any kind of vertical shear to create perturbation here and to destroy this. Okay. So the instability actually does not start, and we remain in this very calm situation where conduction is extremely powerful. So the limiting factor is therefore the viscosity. And the viscosity actually acts to retard, because if we have a fluid which is strongly viscous, viscosity acts to obstacle the propagation of the information, so that the heat remains here. So the strongest is the viscosity, the most difficult will be to create, to destroy this unstable stratification profile. So we can again consider a scale for our vertical velocity, W star. So I'm using now W star to consider just similarly to what we did before with U star. So it's the scale of the vertical velocities. So we can estimate a balance between the buoyancy force, which is going upward, because the idea is that still, since we are in an unstable situation, if you remember the first lesson on stratification, my idea is that this parcel will have to go up. So we are in situation unstable, and I know that my solution was something like this, remember? While in the stable situation, we had the Brun-Weiser frequency. So the buoyancy force, which is actually the term, the buoyancy term in the Z momentum equation, is balanced, or can be, sorry, not is balanced, but can be described as alpha G delta T. Why? Because again, rho prime is equal to rho 0, 1 minus alpha delta T according to the equation of state, where alpha is the coefficient of thermal expansion. So the retarding force, so the force that acts actually to stop or to obstacle this the evolution, because you remember that when we resolve this case, we neglect any kind of force, and we just considered the buoyancy force. Okay. So in this case, we also have friction, and so the friction acts on the vertical with the frictional term which always is present in the, which in this case is present in the Z momentum equation. And this will scale like ni W star H square. So with H, again, we consider the scale of our domain. So if we consider a balance between these two, because these two are the only forces which are present in our system, actually we can find a scale for our vertical velocity. So W star will be alpha G delta T H squared over viscosity. So now we can define a new number, new dimensional number, which is called Rayleigh number, again, capital R, A. And Rayleigh number actually is the ratio between the convection or convective heat flux and the conductive heat flux. So, conduction is practically based on this balance, okay? When we have convection, convection is related to the fact that we are acting in order to help, in some sense, this system to be unstabilized, okay? So, convection actually is expressed by the transfer of the turbulent transfer of the temperature. So W prime T prime, which scales are W star delta T, which will be equal to alpha G delta T squared H squared divided by the viscosity. And this is the convective heat flux. The conductive heat flux is simply related to the molecular effect due to the heat diffusivity. So kT delta T over dz, which we can scale like kT delta T over H. So if we put this term here and we make the ratio between these two, what we will have will be G delta T H cube over KT. Okay? So we have that the Rayleigh number, which practically measure the ratio between convection over conduction, is dependent, linearly dependent by the temperature gradient, is strongly related to the third power of H, and then is inversely dependent to the viscosity and to the diffusivity. So when these two terms here are very strong with respect to this, so it means that or H is very small, or delta T also is very small. So it means that Rayleigh number is very small, and so conduction is winning over the convection. What happened in GFD? In GFD happened that delta T and H can be very, very big. And so when Rayleigh, for example, start to overcome this value here, 1,708, which is not a magical number, but is related to the analysis of this system here. You can find papers on that. So it means that when these numbers start to be, when the Rayleigh numbers start to increase, of course, convection start to be much important, so to overcome conduction. So the transport of parcel is becoming more efficient because it's the turbulence which start to act. So turbulence transfer acts against the viscous retarding processes and start to create convection, and so the convective cell. And for example, the atmospheric boundary layer has Rayleigh, which is order 10 to the 15. Okay, so geophysical fluid dynamics phenomena are, actually have a Rayleigh number very, very big, very, very large. So there should be a nice video. Which explains even better. So this is a video made by Karlsruhe Institute of Technology. So the question is, how can numerical simulation help to understand the greenhouse effect? So they take into account the Rayleigh-Bénard convection, which is actually the system that I described. And so they say that air movement in the atmosphere as well as ocean currents influence our climate by transporting heat, of course. Air and water flows can spread pollutants like oil or other things across large areas by turbulent convection that is difficult to predict. Come on. Give me one moment. Sorry. Okay. Okay. So it is necessary to understand this kind of transport to investigate the influence. And so, in the Rayleigh-Bénard experiment, a fluid is placed between two horizontal plates. Hitting the bottom plate, the fluid warms up and rises, and turbulent convection can occur. Okay? So we have exactly the same system that I explained to you. So we have the two plates. So the bottom plate, of course, with the color, is heated. You see the Rayleigh number, have you seen, is 1,000, more or less. So we have motionless fluid, only conduction. Then Rayleigh start to be increased, 10,000, and this is the result, steady state with convection rolls. But if we increase even more, to 10 to the 7, the Rayleigh number, what happened is that the system start to create plumes of fluid going up, and you start to have turbulence here, because of course this is not so analytically easy described. Increasingly leads to convection and turbulent motions. Okay, so we still have here a central plume, and then we have other secondary plumes, and all the system is not completely mixed, because you will still have this part here, which will remain warmer than the other part, but this is the result. So heat transport depends on the Rayleigh number. If it is low, mainly heat conduction takes place. When it increases and the temperature difference is sufficient, it is replaced by turbulent convection, and so on. Okay. So it's interesting because they said that for those of you who will study the solid Earth, it also enables to understand mantle convection, which causes earthquake and volcanism. Okay, so that's why GFD. This is maybe one of the few cases where this course is also interesting for the one who are making the solid Earth. Okay, so Let's look now the last example. So the last example is similar to the previous one, but is practically a most complex case of convection in the atmospheric boundary layer. So what we have is a plate which represents the ground, which is warm. So it's the situation that I described before. And we have the initial temperature, which actually increases with height, with this law. So T bar is equal to T0 plus omega lambda Z. So we have stable atmosphere here. If it is stable, of course, the temperature will be colder at the surface and then will increase. But what happens is that thanks to the action of the shortwave radiation, we have insulation of the ground, so the ground starts to be heated, and so we have a transfer of heat, which is represented by this Q here, which is actually the effect of the infrared radiation, which starts to heat the first layer, the surface layer from below, and so start to create and to destroy the stratification in order to homogenize this layer. Okay, so it's exactly no, but very similar to the previous case. So we do not have any kind of mechanical action here. We have just a buoyancy action, a thermal action, which act to destroy the stratification and to create a layer which is homogeneous, which is the usual case that we have in our atmospheric boundary layer. Of course, what happens is that if you have a strong insulation at the end, this the temperature will increase so much, and you will have a sort of decreasing of temperature, of course, in height, and then again you will have an increase. But of course, this effect here will start to decrease because you have the pressure which decreases, and so you have all the thermodynamic effect. So, first of all, how much is lambda? So lambda is the gradient, the thermal gradient. So if we express n squared, the Bloom-Weisler frequency, in the usual way, and we have that again, we can write delta rho as minus rho 0 alpha delta t. So this will be G alpha, rho 0 and rho 0 can be neglected, and we have dt dz. Okay? So it means that n, if I call dt dz lambda, which is the gradient, we obtain that n is practically the square root of G alpha lambda. Okay? So, nothing very magic. Okay, so the first condition that we want to analyze is the fact that the variation in temperature, so the variation of the heat content in our layer, is strongly related to the heat flux, which is transferred from the warm ground to the system itself. So it means that the change of the heat content, which is rho 0 Cp delta T, where Cp is the heat capacity at constant pressure, will be in balance with the heat flux, which is provided to the layer in the time delta T. Okay? So if we integrate this expression, so we are a little bit more precise, we have zero Cp. So the variation in temperature in my layer will be the difference between the final temperature, which I call it capital T, and the initial temperature, which is T bar in dz. And here, this is equal simply to the effect of QQ is constant, of course, in time. So we can neglect the two constant. And what we obtain is that H, if we substitute this T bar, of course, with T0 plus lambda Z, okay. So we will obtain H T minus T0, which is actually the difference in temperature that we can observe. So if we are on the ground and we take measure of our temperature, we will see that our temperature will be increased from T0 to T minus lambda H squared divided by 2, which is equal to QT. Okay, so not very difficult, just an integration of this expression of this integral.
First, I don't understand what is the origin of this inequality.
Because what you have, this is a sort of heat balance or energy balance. So what you have is that the variation in temperature, or most specifically in the heat content, and the heat content is rho 0 Cp delta T.
That's the internal energy.
Exactly, in the layer delta Z. So how much the heat is changed in the layer, which obviously relates to the variance of temperature, is equal to what? To the only source of energy which we have at our disposal, which is the Q. And Q is the heat flux, actually. Okay, so Q is...
so where do we put the rho 0 Cp there?
Because the... Why? Because of... well, you can... I mean, what you have is that the usual expression for the heat content is rho 0 Cp delta T, okay? And here, this is just by considering the correct unit of measure. Otherwise, Q is a flux, I think, so it should be like joule over second or something like that. So in order that this can be balanced, we need to put also this expression here. Okay?
I thought we should put just the divergence of the flux integrated over time.
The divergence of the flux integrated over time. Yes, of course, if you like. I mean, this is a very easy way to obtain this this solution here. Okay, so
I didn't think about the rho 0 Cp.
Here, well, I think there is a problem of dimension because Q is temperature over temperature multiplied by meter per second. So is the temperature multiplied by a velocity. Okay, so is actually flux of heat of temperature. And so since we are interested to the heat content, that's why I should put here T, okay, but which T? So the T that I should put here is the temperature which is related to the flux. But what we know, I mean, the parameter that we have in this problem is the heat flux, which is related, which we call Q, capital Q. Is something related to the fact that we have, as we had before, is the expression of the infrared radiation, which is emitted, re-emitted from the ground after the shortwave radiation from the sun has hit the ground. So Q here is like W prime, T prime that we had before. Okay. Okay. So the other condition that we can consider here is that is an energetic consideration, so something more related to the increase of potential energy or decrease of potential energy. But most in particular, we can say that the potential energy in our case is constant. Why? This is an hypothesis that we will demonstrate actually a posteriori of our system. So what we hypothesize is that the kinetic energy is extremely small, much smaller than the potential energy. Okay? So since we have no any kind of mechanical action to our system, we can consider that the potential energy which was present in the initial situation when we had the linear variation of temperature and the potential energy that we have at the end of our system per unit of area, so the same that we represent like integral of g, z, dz rho between 0 and h, okay? So this can be considered as constant, okay? So it's a strong hypothesis that I do, but you will see then at the end it will be satisfied. So if I again substitute the density perturbation here with the usual relation with the temperature, what I obtain is a balance between the integral of rho 0 alpha t gz dz, so this is my density perturbation, equal to 0h rho 0 alpha t bar g z dz. So I'm saying that the potential energy at the end, which is related to a layer which has in its entire depth a constant temperature T, is equal to the potential energy that I had at the beginning when the temperature was T bar. Okay? So I do not have any potential energy gain or loss in this case, as we had in the other case, because we are continuously including energy within our system. So even if there is a loss of energy or potential energy, this is in any case supplied by the fact that the ground is constantly warm. So solving this, again considering T bar equal to T0 più lambda z, and making all the possible computation, which again are very easy, what I obtain is that the difference between T and T0 is equal to 2/3 lambda h. So it means that the final temperature T is equal to the, for example, at the surface, is equal to the initial temperature T0 at the surface, which is here, plus 2/3 of lambda h. But what is lambda h? Actually, lambda h is exactly the distance, the difference between the temperature T0 and the temperature T bar at z equal to h. Because if I put z equal to h in the initial stratification profile, I have that T bar will be here at z equal to h will be T0 plus gamma lambda h. So the distance between this point here and this point here is lambda h. So if I take 2/3 of lambda h, I have this expression here, and this expression is here, of course, is 1/3 of lambda h. So the surface temperature has been increased by 2/3 of lambda h, and the temperature which I had at the beginning at z equal to h at the top of my layer has been decreased by 1/3 lambda h. So if I compute T0, if I compute the average temperature at T equal to 0, which means make the integral between 0 and h of T bar dz divided by h, which is very, very easy because I just have to put that expression here, I obtain T0 plus gamma lambda h over 2. If I do the same at T equal T, so after that the erosion of my stratification has been reached at certain level h, so this will be 0h T dz over h, which is simply, so T is T0 plus 2/3 lambda h, and so I obtain T0, of course, 2/3 lambda h because it's constant. Okay? So the difference between the final average temperature and the initial average temperature, which is the difference between this expression here and this expression here, so the delta T in time t is equal to lambda h6, which obviously is positive. So it means that actually at the end this layer here has been on average heated by a value which is 1/6 of the temperature difference that I had at the beginning between the surface and the height z equal to h. So as a final step, what I can do is to solve my system from these two equations here, and what I obtain is that h is 6 qt over lambda, and t is equal to t0 plus 8 lambda qt over 3. So as before, I found an expression of the mixed layer depth, which increase in time, but if you remember, in the ocean it increased, so ht was t to the 1/3, while in the atmosphere ht is t to the 1/2. Okay, so actually it's faster. Is also, like here, is of course proportional to the driving force, which is q via a square root, and it is inversely proportional to the stratification, actually to the parameter of stratification, which is given by the density, the temperature gradient. Okay, so if we calculate, and this is the last point, we calculate the value of kinetic energy and potential energy, we can say that the vertical velocity, which scales as alpha g delta t h squared over n. And if we have that the kinetic energy is order of 1/2 rho 0 vertical velocity squared multiplied by h, and the potential energy is rho 0 alpha g t minus t0 h squared, and I use the expression of vertical velocity, which is related to the specific problem that I have now. So this is given by the Rayleigh number. Okay, so in the case of the system that we are analyzing now, we have that this is equal to k alpha g h q to the 1/3. So inserting this term here within the kinetic energy here, and making the comparison between kinetic energy and potential energy, what is obtained is that the kinetic energy, the ratio between kinetic energy and potential energy is like scale like nt to the minus 2/3. So scales like the product of the Brun-Weisela frequency multiplied by time to minus 2/3. So since this term here, n, is, the frequency n gives rise to times which are order of minutes, as we said last time. And we can have that this number here actually is much smaller than 1. We will see that the kinetic energy will be much smaller than the potential energy. Okay, so it's a very, let's say, it's not important that you understand all the step, but what it's important that you understand is that if we reconsider the expression of kinetic energy and the expression of potential energy according to the specific case that we are solving, their ratio is scales like this term here, nt to the minus 2/3, and this term here in GFD phenomena, so in case like this, is much larger than 1. Okay, so this term here is much smaller than 1, so being at the denominator, we have that the kinetic energy is much smaller than the potential energy. Okay. Okay, so this is all. Thank you for your attention. I hope you liked the course, even if it was like a sort of fast run, and especially maybe I won't ask you the last because every time I would always spend more time to the second exercise, but this is not part of the exam, so I won't ask. If you want, you can, okay, of course, study it, but this will be not one of the answer of the question. But the first one, yes. Okay, so the one related to the surface of the ocean, it will be. So then it's not said that it will actually be, but it is possible that it will be. So that's all. If you have any question, you can reach me by email. And
3 questions.
3 questions. Wow.
Later or not?
Well, you can.
The first one was related to the problem with the wind stress on the ocean. So in that problem, we suppose that the ocean started in a static configuration. So the wind stress had no effect on the mean motion of the ocean.
Yes, we can say like that.
Can we understand that from something of
Well,
problem?
the fact is that the problem that we explored was, in some sense, you cannot consider also the transient condition. So you move from a condition where you have a stratification to a condition where after some time something has happened, and you have practically homogenized the layer. So of course, if you want to see this from a broader view, you could also consider that there is an Ekman layer. You can also consider, as you said, that there is a current. So the fact that I have a wind stress over the surface, I can also consider that there is a movement of layers. So from the very simple laminar case where you have that if you have one layer moved by an external force, the layer will go to take that force and move in a very simple, if not the same, because if you can consider like the co-wet boundary layer, okay? And so you can express like a sort of linear velocity gradient. Of course, all of this will be present. And but what we can consider in this case is that, I mean, the idea that we wanted to show is how to actually solve this problem just by considering the major driving that are present. Okay, so you are totally right. Of course, there is a vertical shear in the velocity, because of course there will be. But that problem is like you are just looking at one single water column, and in that case, all the aspects related to the dynamics and to the kinetic are included in that coefficient m that we just consider as a number.
So I don't understand. We are studying the transient, the start, or just?
We are studying just the effect of the wind stress over the stratification. And so what you can say is that you have that the evolution of the system, you have started like here, when you have t equal to 0, you will have that h will be 0, and then you will increase h according to t. The same in the other case. So of course, in this evolution in t, you don't consider any kind of dynamics, any kind of effect due to velocity and so on, but just only the effect related to the wind stress in one case or to the convection in the other case.
So it's always a balance of terms.
Yes, yes.
Because I knew that if we want to study the dynamics, I mean, solving the equations for convection, for example, we must use always a linearized version of the equations, which is not possible if we allow perturbations to grow indefinitely. So
yes,
in that case, we can only study the conditions for the onset of the instability of the convection.
As we did yesterday.
So this is another case.
Yes, it's a very simplified case. I mean, it's something that you really consider like a sort of exercise just to understand. In particular, what the first question was: has the Monod-Nabucov length a physical meaning? And what we obtain is related to the fact that is the distance of the vertical edges. And the second one was to consider how just taking in account the wind stress and the response of the system, which is the instantaneous value of the mixed layer. So it was really as I said, you can put together different aspects of the reality and complexify the reality as you want. But of course, in this occasion, it was not possible. I mean, we are looking just to one specific aspect of the reality.
Okay. And the other question was, what is there going to be in the course of dynamical oceanography?
Ah, what is going to be in the course of? Don't you have the syllabus?
Yes, but it seems to be very similar to this one.
No, I don't think. No, I think they are going to make, for example, the circulation in the ocean, how to measure the ocean. For example, I knew that in the past they did, for example, they applied GFD to explain why we observe the westward intensification for example, in the Atlantic Basin. So if you apply the GFD equation to a box which is forced by wind stress in a particular condition, you will see that there will be, just by geostrophic consideration, an intensification on the westward side of the basin, which practically explains why the Gulf Stream is constrained to the west part of the basin, like the Kuroshio, for example, in the Pacific. And then, I don't know, I mean, maybe also some ideas of general circulation. Thermaline circulation, we never talk about thermaline circulation. So, have a look to I don't think it's...
Yes, I don't look at it.
Because otherwise, this is something that you can, I mean, because sometimes I know that the courses can be changed year after year. So I had an idea of what the ocean dynamics course was made like 2 years or 3 years ago. So I don't know if in the meanwhile they have changed, because there should be a committee which analyze the different courses in order that there are not two courses equal. So ask, I don't know who is maybe Gacic is the...
I don't remember.
And the third question?
Last question. I forgot the second.
I got to wash my hands in case.
Very good. What's my name? Non so più come mi chiamo. Io no, grazie. Zappacosta. Esistono equation.
Il mio computer è arrivato.
No.
Sai perché è arrivato?
Guarda, non ti dico le parolacce solo
Sapete perché è arrivato? Perché la tipa che ha cominciato il dottorato.
no, quindi sono arrivati una barca di soldi.
Il computer era per lei e lei ha deciso che vuole tornare in Italia.
Ma prima anch'io da decisione così. Cambio per un prezzo di soldi.
Ma stai guarda come finisce.
Meno geologo.
Ciao.
I soldi perché fanno essere utili.
Noi che non studiamo niente.
Siamo noi che mandiamo avanti.
That's an over paper.
Ciao. Bye.
I thought this was